All right, let's look at the chapter 12. This would be, if you don't know too much about C++, this would be one chapter that you do want to pay attention to. And this is one of the, obviously, the core features of a C++ that allows you to use object-oriented programming. And that is also called OOP. And this is what we focus on in this course. And now, what is OOP? So OOP is general idea is this is you try to make a program by designing the objects that you will need in your domain. Whatever that problem is, you try to model the problem with various different kind of objects. It's like how we see the world. You have, let's say you're building a house, you're trying to do some kind of a model, 3D modeling, and then you would want to have sort of different parts of the house. The house has rooms and bathrooms and bedrooms and things like that. And then you think of a car, right? A car is composed of an engine, a couple of wheels, and so you try to think the world in terms of objects, and then the objects have properties and also behaviors, and then they can interact with each other. So that's kind of the basic idea. Now the OOP offers a number of sort of a benefits, if you will, when it comes to programming. So one of them is called encapsulation. Encapsulation is essentially the packaging of data values and functions within an object. Now, I'm using sort of the terminology that as defined in this textbook, and there can be sort of a different understanding out there if you read other articles. But I do like what the textbook sort of a point of view. And at the end of the day, it's not that important to get a concept 100%, but as long as you can understand what they are, and then it's kind of that's enough. So the encapsulation, here's an example. Let's say you have a loan account object. Now the loan account, that's your custom type. That's like, well, of course, it's not what's defined in this language. So that's your own custom type. In fact, that's a class. We're going to look at that. Class is essentially a construct in the language that sort of embodies the OOP concepts. So this is, we're thinking of a banking application, and let's say this loan account object, it has variables, and it also has functions. So far we have seen we use variables in a function, right? And then maybe outside a function. And then this is, we're putting the variables and functions together. So this defines, at least from this point of view, for this specific application, we have these variables that are defining the properties of this object. We'll say this object has these variables that are associated with it. And is, as you see, is a composite of two variables here. You probably have sort of a double here, and you have a double there, and both may be double. Then, then, well, this number, the way it's displayed here, obviously the C++ language does not support this kind of, number with a currency symbol here like this. This would be something you would display, but it's not necessarily what you put into the system as part as the value of the variable though. So this is again just for the purpose of a display, and then you have the functions that that define the behavior, what you can do with this object, essentially to manipulate the variables and do certain calculations. So obviously here you can do credit operation, debit operation, and calculate interest. Now, of course, this is a simplified example to illustrate what encapsulation is. You put the variables and functions together, and the variable is also called the state of the object. And as the consumer of this object, use your functions on this object, and then your variables may change, may throughout the application. And of course, the responsibility of these functions, you have to make sure that the state of the object is still valid every time these functions are called. And then a related concept is called data hiding. So sometimes casually people talk about encapsulation when they're actually talking about data hiding. So data hiding is essentially the ability to make data values of an object inaccessible to the consumers, generally speaking. So how does it achieve that? We're going to look at how that's done, but this is we're talking at a higher level. And then the classes are sort of C++ solution to OOP. Okay, but the OOP, of course, is not specific to C++. So here's the same loan account object. And these variables, the way, just of course, generally speaking, sort of the recommended approach, your variables, most of them would be inaccessible to the outside or the consumers of your objects. But of course, you want to be able to manipulate them in your own functions that's part of this object. And so, and this is called the member variables. These are called the member functions. Sometimes if you're using different language, they're going to has a different terminology. This could be called fields. Sometimes they are called fields. And then the functions or member function can be called methods. So that's data hiding. That allows you to hide your state from the outside, from the consumer of your object, but then they have to go through the functions or behavior that you define. That basically there are the ways you can manipulate the object. Of course, then you can obviously do sanity check or verification and make sure that whatever has been done, it does not violate the state, does not render the object sort of invalid. Now, another benefit, a main benefit of that data hiding allows you to do is by providing sort of a public interface to the consumers through the functions, and then it allows you to restructure your code, perhaps for performance reasons, perhaps for clarity, perhaps because now you added one more type of account. You realize some of the things are common, and you may extract commonality into a different part of the program, but then you can still keep the interface remain intact. Well, of course, this interface can evolve as well, but then it doesn't give you the flexibility to refactor without changing the public interface of your objects. And then the benefits of data hiding, as we have kind of just talked about, one of the things is it helps you maintain the integrity of an object, because the consumers of your object have to go through the functions that you provide to them. And of course, then you can, in your own function implementation, and then you can basically try to maintain the integrity, make sure the state of the object is still valid after each invocation of the functions. And It also allows refactoring, and we just talked about the refactoring. Basically means that you try to improve your code, improve the structure. Um, Maybe not, you used to have a huge block of code that you now you have that already implemented in another library. Then you're going to use that library instead. Simplify your code. So anyway, refactoring. Um, and sometimes what we'll say refactoring is for is to reduce the entropy of your code base. The just naturally the code base becomes chaotic, like the natural world in physics, right? So the entropy needs to be reduced from time to time through refactoring exercises. Sometimes refactoring is necessary because your code is not very well written, it's not very testable. So to refactor it is to allow your code to be tested. Um, we don't talk too much about the testing in this course. That would be a sort of a separate course. I would, that if you are able to access a curriculum on testing, and then I would recommend you really study testing. That's sort of integral to software development. You have to have testing. Now, the next thing is it also allows you to inject extra code into the interface functions. When we say interface functions, it means those functions are accessible to the consumers of the object. You may also have the functions that are not accessible, sort of a private to your object. But again, those things that are accessible from outside, they are the so-called interface functions, because that group of functions comprise an interface. That's what sort of because the outside world can interact with this object. And so you can inject extra code in there for maybe you just want to log, or print stuff out for debugging purposes. Or maybe you have some code that's trying to audit what's been done because there's a critical operations, for, especially in banking situation. So you can do all of that without impacting the public interface of your object. Then I just kind of mentioned the debugging makes it easier because not only because you can inject that code without, the consumer to modify their code, but then also the that it allows the sort of the direct access to data variables, because direct access to data variable, that is not a good idea, because the debugging also could be a little more difficult. It kind of has to do with how the debuggers implement it, but this is just a trivial point. Now, another really important OOP concept is called inheritance. We're going to talk more about inheritance, of course, later on. This chapter is more of an introduction to the classes, but then we're going to actually look at those aspects in more details later on. Now, inheritance. Well, think of a family tree, right? You have ancestors, parents, and kids, right? So genetically, some of the traits are inherited. It's kind of a similar concept. So say we have a bank account that holds some common functionality. We have any kind of bank account, we have a balance, we have interest rate. And then there's some behavior we define that you can operate on those variables. Now, let's say you have two different kinds of accounts. You may have a loan account, you may have a checking account, maybe you have a savings account, right? There's different accounts as the products from the bank. And the inheritance allows you to build some kind of structure that, because these two accounts are so similar, there's a tiny little bit difference. For example, a checking account, we define what to do with overdraft, right? There's no overdrafting when it comes to loan account. It just comes down to, you may have a limit on the balance, but the thing is, there's a certain things that are unique to different types of accounts. But then for the most part, they're all bank accounts, right? So that's kind of really what this allows you to do is then you say you have these two objects that are inheriting the features of a bank account. So if you think of these as the classes, and that was sort of the C++ utility implementation of OOP concepts, again, the classes are class, or the reason it's called a class is because that's a class of objects. We'll talk about objects here because in the end of the day, you're manipulating objects. So the classes are just a definition what you can do with the objects. Um, and that is actually a common concept. We call this a C++ or some other language. So this is the same thing. It's called inheritance. And a related concept from inheritance is that because of inheritance, you can define a behavior from the here. Let's say this is a base or parent object, and that behavior could be different depending on at runtime you have a sort of a child object here, right? Either is loan or this is a checking, and then they calculate interest. They are implemented slightly differently, right? So you could potentially, here's a little bit block of code. What you do is, let's say you have a pointer that can hold a bank account object, and then you have actually defined two objects, one for loan account, one for checking account, right? You have a debt and a cash, and this pointer, when you access the calculate interest function on that pointer, now this pointer may not even be implemented. I mean, this function may not be implemented here because then they are actually implemented in these concrete account types, and then in that case, so at runtime, depending on the actual object, I mean, even though the type, well, the compiler will not see what this thing is, but again, it only sees this is bank account. And then, but again, yes, you can calculate interest on the bank account, but then the actual behavior is not defined until you actually have an object that says a loan account. If it's a loan account, then the calculation, this is basically doing the loan account interest calculation here versus the checking account here. You calculate interest, which is actually an interest as a credit to the customer. And then in terms of loan and interest, it's charged to the customer. So they're kind of a different things. One is the interest for the bank, one is for the interest for the customer. So the behavior differs at runtime. That's kind of really what's so-called polymorphism. And of course, we're going to look at more concrete examples in the later chapters when we get to those. So take a look at a couple of the terminology that we'll talk about in OOP. A class is a user-defined data type. A class really means it's a class of objects that you're trying to model in your application. And then, so the class has members, and the members could be variables or functions. And the member variables functions are also called fields and methods. And variables of a class type, when we say a class type, actually, when it comes to C++, there's actually a few class types. But we, as an example, there's a struct. Now, that's a structure that's coming from C. However, the struct in C++ is not the same as C. It's almost like a class. You know, functionality-wise, it's pretty much the same. There's a the default behavior is a little bit different because the purpose of what structures are for. And so right now in this here in this lecture, we're not going to talk too much about structures, but let's focus on classes. So variables of class type store objects or instances. So sometimes these names are used interchangeably. So we sometimes say you have created instances of a class or instantiation of a class. And then, of course, the result of instantiation are the objects. So OOP is a programming style that's based on the idea of defining your own data types. If a programming language doesn't allow you to define your own data types, it's not that much useful, don't you think? Okay. So core OOP concepts include encapsulation. Encapsulation we talk about is the ability to package your variables and functions together, they become a unit of logic. And then you have data hiding, inheritance, and the polymorphism. We just explained those. So when it comes to C++, how do you define a class? So there's a keyword here, class. Essentially just call it, class, and then you give a name. And then you hear the members when you say, okay, so you got the variables and functions, right? So the members could be private, protected, or public. Now, private members means they are only accessible to the members of this class only, not outside the class. Not outside means not, some other entities that are defined, not part of this class. Now, protected are those members that they're accessible to the members of derived classes too. So when we talk about inheritance there, so you got a base class at the top, and then you have this different bank accounts. And those are the derived classes. And so they can access the protected members of the base class, right? And so we can talk more about this when we talk about inheritance. And then public. So public members, obviously, the already is what the name says it all, is they're accessible to anybody, right? Any other entities outside this class as well. So the non-members as well. So now, of course, this is in terms of the accessibility, the members of this class, obviously, like the member functions can access all of them, right? and the public is the one, all those members, they can be accessed outside of the class as well. So here's a simple example. So let's say we're trying to model a box. Maybe you have a tracking application, that for moving, it's a moving company. Okay, we need to make an application and deal with the boxes, right? So a box, let's say we have a couple of member variables defining the dimensions of the box. You got length, width, and height. This M underscore is simply just a convention indicating these are members. And so let's say you have a member function here that's actually public. And then then you calculate the volume, for example. And so here's a simple class. And then how do you make an object of the class? So you make an object of the class through constructors. Constructors are special member functions. This is how they look. So first of all, here, let's look at the simplest one. This is as you notice, the function name is the same as the class name. And there's no return type. There's no parameters. And no parameters here means this is called a default constructor. Of course, you can take parameters. So the default constructor is the one that has no parameters. And if you don't provide it, typically this will actually be generated by the compiler. So actually, what I wrote here is it's generated if no constructor is provided. If you provide a constructor, the compiler backs off. It will not generate anything when it comes to constructors, because now you realize, oh, you know what you're doing, so I'll leave it to you. Now, so here, let's say we define a constructor would take those dimensions as parameters. And then in this case, let's say I still want the default constructor. Then if you do want it, you want the one generated by the compiler. So you can use this format, this syntax, equal to default, which is a keyword. And by doing this, you're asking the compiler to still generate that one, okay? Now, how do you implement the constructor? So the constructor needs to initialize your member variables. Your member variables needs to be initialized, of course, for that to be a valid object and to be useful. And your box, you do want to know the dimensions of the box, right? The object needs to hold on to remember the dimensions of the box. And so this constructor actually allows you to specify these 3 dimensions, and then we need to initialize the member variables. Remember, this m underscore, those are naming convention to indicate they are actually member variables. So, and this particular format with a colon here, and you got a comma separated list of initializers. The member initializer, now this is not much different from what you normally see of a variable getting the initializer with this braces, right? And so except here, of course, we're using the variables that are defined as members of the class, and then we're trying to initialize those member variables with the parameters or the arguments passed into the constructor, okay? And then you see a box, colon, colon, box. This is basically saying the body, the definition of this constructor is defined out of a class. If you just define this inside the class, like right here, and then you could do that. Here you see a signature, right? And then so you can actually define right here, it would be just inline inside this class as well. That would be fine. Then you obviously don't need to have this class name with the colon prefix. This looks like this resolution scope resolution operator, just like what we talk about in namespace. It's a similar concept because a box. Now the class name is not a namespace, but it has its own scope, right? This is telling the compiler this function belongs to box class. Okay. All right. So, and there are cases where you want to be careful because if your constructor has only a single argument, now single argument means either it takes one parameter or it takes multiple parameters, but they take default values. So when you call the constructor, it allows you to specify just a single argument, right? In both situations, we'll call them the single argument constructors. The single argument constructors could be used by the compiler to implicitly convert one value to an object of your class. And that could lead to unintended consequences. So as I kind of have repeatedly said, it's important to make your intentions clear. You do want to clarify. Don't try to avoid too many of the implicit conversion. There's a few places where implicit conversion is well understood and is conventional, and then you do it. But otherwise, just to avoid bugs that it's unintended, and making intention clear. So sometimes, if you don't hear, you see this keyword here, explicit. What this purpose is saying, this is preventing the compiler from doing an implicit conversion to this type. If you are passing, this is saying, if you want to make a object or box, you need to just invoke this constructor instead of having the compiler do an implicit conversion. Somehow this double could be just a box object. So anyway, so that's really just saying you have to explicitly invoke the constructor to actually make an object if you want to pass in a double, but the compiler will not try to implicitly convert that in an expression. So when you define constructors, sometimes, well, actually most of the times, one constructor is not enough. You provide different flavors, and to make it easy for the consumers of your object, your class, to actually be able to construct an object of your class easily. So there's you typically define different flavors, just make it convenient. Now, so while you're defining many different constructors, and they can actually use each other, and so basically, one constructor can delegate to another constructor for the initialization purpose. For example, let's say we want to sort of make a box of sort of a cube. You just, all the three dimensions are the same. You have this side that's passed in, and so then here this is delegated into the other more full-fledged constructor that allows you to specify all the three dimensions. Here we're just delegating to it by calling this box constructor with the initializer with the three parameters. Okay, they're all the same in this case. There's another special type of constructor that is to construct an object from another object of the same class. So typical format, as you see, is actually this other object that you're trying to copy. That's essentially what it means, is that you're constructing this object by copying another object of the same class. So this is called the copy constructor. Typically, this is defined, the parameter is defined as a reference to const. But this is how, of course, we don't want to modify the other object you're trying to copy. There are also some technical reasons why that's not desirable. But anyways, so this is the copy constructor. This is a you can basically make a box object out of another box object. And so the implementation here is straightforward. You basically use the other constructor of a box, right? You can just initialize the members this way with the initializer by delegating to the other constructor. Now, in fact, things like this, if it's straightforward like this, you don't have to write it, because the compiler will generate it. So in fact, the compiler usually does a better job than you do. So you just leave it. And but there will be occasions where you do want to define your own copy constructor. That's sort of the smaller cases. So then here, you may also say, I don't want the consumer of this class to actually be able to copy. So then to do that, to tell the compiler, say, don't generate it, okay? Then you just say equal to delete. And then so the delete there, so basically compiler will not generate it. And and this behavior actually propagates. So if you have deleted a copy constructor for this class, and then any other class that uses this class, maybe as a member variable or some, for example, right? So then they will not be able to have a copy constructor either, because this part of that object cannot be done, because this is not copyable, okay? So it propagates this. Now I put this thing here. We're going to talk more about this, because this is the operator overloading here. You see the operator keyword with the equal sign. That's actually the assignment operator. And typically these two things go together. And this also is generated by compiler too. And if you're deleting the copy construction of, you usually just want to delete the copy assignment as well, because okay, they cannot do the they cannot use the constructor, but then they can still use the assignment. Then what's the point? You still not, you're allowing them to make a copy through assignment. That's not good, right? So typically, if you do want to prohibit the copy construction, preventing the compiler to generate them, and then you need to delete both. So just include this here for completeness, and we're going to talk more about operator overloading later on. And then a common set of functions in your class are going to be dealing with access to your member variables. And these are called accessors and mutators. Accessors are called, the ones that, for example, get length to read the value of a member variable. Or you may want the consumer to be able to change it, and so use a set length. And then, of course, you may do some checks, make sure that the value is valid. or sometimes it will have a more complicated logic here. But anyway, so you may allow them to change the value, and that's called a mutator. And then because the naming convention here, we sometimes call these just simply getters and setters. By the way, if the type is a Boolean, we don't normally say get a Boolean variable. There's a, but you usually say it's, right? It's just more grammatically correct, okay? But that's still called getters and setters. Now, there is a special thing called the this operator. The this operator is made available to you in the member functions automatically. So in the member functions, well, to be precise, non-static, we're going to talk about static. Non-static member functions, you will have access to the this pointer. This pointer is basically provided to you that's this pointer points to the current object this member function is being called on, okay? So how is the member function being called? That you have an object and you call the function on that on that object. But so that object, you can access it through the this pointer. So this is a keyword, okay? This pointer is a raw pointer, okay? So you can use this arrow operator to access the members if you need to do it this way, and so this is equivalent to if you just omit the this with it, you don't have to access through this pointer, but it's equivalent. But then when you define this, especially inside the function, inside the class, you can just use this member variables directly without. But then there are cases where you do want to use this pointers, but then so we're not going to elaborate too much on when you might use the this pointer, but this pointer typically is very useful when you want to just return this pointer again that allows you to chain the member functions, because once the function returns, it returns this object and then allows you to continue to invoke the next function, or you may return a reference to this object. Then you can use the dot notation to invoke. So those are just some of the syntactical ways and that people may do to make the class more easy to use or more fluid. And let's talk about const. So const member functions, what are they? Interesting, right? You have a const right after the function header, right after the parameter list. Interesting, right? So this const, you will not be able to do with the free functions outside of a class, and those standalone functions. This is just not valid. This const here, really, this is talking. So we'll talk about this pointer to the current object. This const is basically specifying the constantness of this pointer. Okay, so if you see a const here, this is called a const member function, and in that case, this pointer is a pointer to const object. So the current object through this pointer, the current object is non-modifiable. Okay, so that means that you can now modify the member variables from within the const member functions. And then that would be a typical case. Let's say you have a getter, so that would be obviously a const member function, and then you have a setter that cannot be const because you are trying to modify the member variables. So there are some complexities with the const. We need to make sure that we're using const properly. So first of all, the const objects are immutable. Means you cannot modify the state of the object. You cannot modify the variables of the object, one or another through functions or not. And so if you have a const object, and then you cannot modify. But then what the things you can do with those objects, you can only call the const member functions because they are guaranteed to not modify the objects. Yeah. So that's one thing to note. And this pointer in the const member functions is a pointer to const. So as I said, when you add this const at the tail of this function header, the member function header, and that is really specifying the property of this pointer. That turns the pointer to a pointer to const, right? And not only this, the member variables. So effectively, this is what the result of that. Then the member variables become the references to const. Okay, if you're using this pointer, is that basically is a pointer to const. If you're using the member variables, they are just like reference to const. Okay. Const is a part of a const member function's signature. So this is not a return type const thing, right? This is in the end of the function header. This const is actually part of the signature, means that is what compiler can use to differentiate one function from another. So you could have a function that's a const and the other function that's non-const without the const keyword, but everything else is the same. These two functions are considered different, right? So you can do some overloading here. There are situations, so we're not going to talk too much about those situations, but when we encounter them, that will be explained. There are some occasions where you want to cast away the constness, sort of overriding that default behavior. Of course, you have to know what you're doing to, the compiler, the language is trying to protect you from making mistakes. But then if you do know what you're doing, sometimes that is necessary. So you can use this const cast operator. This is an operator. So recall we have the static cast, right? One type to another. Const cast is dealing with casting of the constness. And there are two forms of the const cast. And you're casting the result of an expression to say a pointer type, or maybe casting that to a reference type. Okay, so you can do them either way. So when you do the const cast, is that as you see, the end result of this, regardless whether the expressions are const or not, the result of this, there's no more const, right? So you're getting non-const pointers or references out of that. That's really what this const cast would provide you. And then there's another way to be able to modify your member variables from your, so we just said in the const member functions, you cannot modify your member variables. You can provide exception to certain variables. If you do know what you're doing, then you use this mutable keyword in front of that member variable declaration, and that makes that variable mutable, means that even in const member functions, you can modify them. And so mutable member functions can be modified even inside the constant member functions, and why. And so we're not going to dive deep into this, but there are occasions in the case of a debugging, logging, caching, and thread synchronization. I kind of include a couple of cases here. Of course, the real world application that do need to have those things. So the mutable has its place, but you're not going to be using that for most of this application that you write, at least not for this course. There's we'll talk about the access specifiers, public, private, protected, right? And you can provide access to your members, basically to the entities outside of your class. That's called the friends of a class. Okay. So you can say this function. So here you declare something as a friend inside the class that you are that's being the subject we want to access, but we're allowing access to everything in the box. So all members of box is going to be accessible to this function. And so here is simply just a declaration with a function prototype here, and then you'll have this function defined outside, obviously, because it's not a member function. And then you can also allow another whole class can access this class members. So this will allow the members of a carton to access everything in the box. Well, one thing to note, this is not like a real world friendship, because the friendship here in this language is not mutual, it's one directional. Okay, so you're giving access to those friends, but you do not get to access those friends. Like, for example, Box will not be able to access members of a carton, well, except the public interface, of course, but there's no special privilege provided to Box, because just because Box considers carton as a friend, carton does not consider Box as a friend. Okay, so that's that's the situation with the friends of a class. And okay, well, what's the deal with the class objects? Well, how big is it, right? If you define member variables. So the thing is, the size of an object is at least the size of the sum of the sizes of the member variables. So if you got member variable, an integer, you got a double, you got another whatever object there. And you can add up those sizes together. So the size of your object for this class is going to be at least that big, and oftentimes bigger. That's because there's a thing called a boundary alignment. What's a boundary alignment? By default, the compiler aligns the class members. We're talking about the member variables on their size value. So, for example, if you got member variables bool and char, they are going to be aligned on a 1 byte boundaries, meaning the address, well, the address that we assign these variables are going to be sort of a modulo 1. And so essentially, that's kind of, so of course, these are things that are more flexible because they're a 1 byte boundary. Let's say you have a short, they're going to be on a 2 boundaries. And so basically, for example, if you have address 123, that will not be, it will not be used. It will not be allocated in that on that kind of address. It will be, you have a 124, yeah, that's fine. Okay, so it will align the address. So where is this variable going to be allocated in memory? So it's dealing with addresses. The address itself are the reason it does this, it has to do with the performance for the most part. So this behavior, though, can be modified. So you can actually modify, I just kind of mentioned this thing here, and we're not going to go deep into it. So you can modify with this align as specifier. This is another piece you can put into your class definition, for example, or in front of a member variable if you want to align this somehow differently. And you can also get the alignment of an object through this operator, align of operator. Okay, align of operator that you can. So if you're dealing with a low level, like your dynamic memory management, then this is one thing you need to be aware of. This is going to be relevant. But for the most part, you don't really have to worry about this. Okay, static member variables. So far we have seen the member variables and member functions that are non-static. Okay, I wish there's a better word for non-static. But again, there's only static and non-static, okay? So those member variables and functions, they are, well, at least for the member variables, for every object, there's a copy of those. And contrast that with the static member variables. If you have a static member variable here, for example, you got this s underscore object count, and s underscore is just simply a naming convention here to indicate this is a static member variable. And inline here means you're initializing this static member variable here. That's what this keyword does here. If you're defining this outside of class, like you only declare here, but then define it outside, initialize it outside, then you don't have to use inline. Inline means it's part of this class inside. So this static member variable, there's only one copy of this in the whole entire application when you run it. Doesn't matter how many objects you make of this class, there's only one copy of such static member variable, okay? So let's say you have 3 box objects, okay? And they all have their own length, width, height member variables, but then there's only just one static member variable, which is the object count that's remembered for this class. And then, of course, your member functions can access this as usual. Then static member functions. So the member functions can also be static. If your member function, this function, let's say you're only accessing the static member variables, or basically as long as it does not need to access the state of the object or the non-static member variables, it does not need to access them. And then typically you should define your this function as a static member function. Maybe it's some kind of a helper. So this example, for example, here we're not accessing the member variables of this object, but we're accessing whatever we need to access is coming from this parameter here. It's passed in. So it's not really accessing the state of the current object. So there's this function is not tied to a particular object. So it's a static, right? There's another special member function called destructors. There's only a single destructor for a class. A destructor is a member function that's invoked automatically when the object goes out of scope or destroyed by explicit delete, okay? And so here, the name of the destructor, you have this tilde in front of the class name. And by the way, this whole thing is the name of the destructor. You don't really directly call the destructor. If you do want to directly call it, the name of it is the tilde, the name of the class. That's actually, this whole thing is the name. So of course you don't have a regular function that starts with a tilde. So this is that's what marks it special, just to tell you. Anyway, this is kind of indicating this is a destructor, and this will be called automatically. And then what do you do over here? Like you deallocate your pointers, for example, if you're using raw pointers. If it's a smart pointers, you don't have to worry about them. How are the smart pointers implemented? Smart pointers are wrapped the raw pointers inside, right? And they use destructors to actually just deallocate the objects they point to. So that's really what they are, essentially what they do. That's kind of just a simple wrapper. And so, yeah. Now let's take a look at this truckload example. So it's a bit of a comprehensive example in the book. And I thought this kind of illustrates a lot of the concepts. And so let's take a look at the code actually. Well, let's kind of just take a quick look at the files. So is this X1217. Typically, when you try to understand a program, you start with the main function, right? This is where the logic starts. This is where the execution starts when you launch the program. So what we see here is we see a truckload. And here's the thing. If you don't have access to the design of the program, like nobody explained what this is about, you're just reading the source code, then you have to read the code and then just basically go from figuring out, look at the main function and try to see what this is trying to do, and then try to understand what each one is. But typically, if you get access to some code, you will have comments and they tell you what they are about. But when you produce code, actually, when it comes to OOP, you actually, do a bit of design and you draw diagrams. There's actually a standard for drawing the OOP related diagrams. This is called UML, Unified Modeling Language. We may get to use UML a little bit, and I'll show you some of those things. But, so for right now, what you see in the book, this is a sort of illustration for understanding the code structure. And we use this box. Typically, this notation, the way it looks like this, it's more of a borrowed from that UML as well, but it's not exactly that. So UML is a kind of standardized how the symbols have a particular meaning. But here, let's say it's just an intuitive diagram. So, for example, this here, we're trying to understand this package class. And so actually we see there's a bunch of files here, right? Let's kind of look at these files for this program. Yes, there's a package. Here is a header. By the way, I'm doing this in non-module version here, and just to make it easier. And then we have studied the modules, and so because the IDE support, everything is just a little bit harder for modules, and so for this example, I'm just using a non-module version. So we're looking at the headers, but really, when the modules are mature, and that's really what you should go for. No longer make headers, but for right now, we're doing headers. And this is obviously typically what you see in a header is called the include guard. So that when this header is included in multiple places, it will only be rendered once. Okay. And so we have this. You see, just kind of just have a little overview. And by the way, the IDE, every IDE will have something like this. Let's say you have an outline. It's kind of helpful when you have an IDE. And this is a Visual Studio Code, and you can install this for Windows too. I did not mention this much for Windows user because you've already got Visual Studio. Okay. So there's this thing called the outline. Outline, it gives you a very a very quick view of the outline of the file. So what we see is in this file, we've got a package class, and then there's a bunch of, see there's, this is the member functions, and they have member variables here, okay? So you have a box, and next is a pointer. So here's a raw pointer, by the way. And then we've got another file box. Okay, so here's the thing. By just looking at these files, you don't know the relationship. There's no structure here. You've got a bunch of files, right? So, and this is where these diagrams come in that tell you the structure. Well, you can try to make sense of them, but picture is worth 1,000 words. All right, so let's look at this, right? So this package, what is a package? A package is a sort of it contains, it's a structure. It's kind of like a little bit of container, we're not talking about the container of many elements. This is a container that contains one element. Well, two variables in this class. One variable is a pointer that points to the next object. And then the other one is really the real thing that's carrying the payload, so to speak. Okay, the package has a box inside. And this box is a shared box. What's a shared box? It's actually just a synonym, it's an alias to a shared pointer. So if you actually just look at this, so what all this does here is essentially just is making an alias of this type. It's a shared pointer. We're talking about smart pointer, right? This is because we want this box object that's wrapped inside this pointer to be able to sort of you can have multiple such pointers pointing to the same object, if that's what we want. And this is what we want, this is what we need here. And so we essentially just made this an alias name called a shared box type. And that contains an object. It's a pointer, points to another object. So as you see, essentially this has got two pointers. One pointer points to the payload. That's really what this package is contained. It contains this object. And then it also has another thing, is a pointer to the next object. And of course, if we got another object of this, which that it points to, and then it will have a next. So by using this next pointer, it makes a it's called singly linked list. So we're making a linked list. Now, there's no limit to how many such objects we can make. Well, your memory is the limit, but practically, so essentially you can think of this as a no limit. You can make this linked list as big as you want. So you can grow. So if obviously you can grow by adding more objects to this chain, right? And so this is really what this package is for. Package is encapsulating a node in this linked list. So sometimes we'll call this a node in this linked list data structure. And this node has a payload, the object that this element, this node contains. Just so happens in this case, we're using this object here for this is what what it contains. And then this next pointer essentially just that's what makes the structure of the linked list. And then if you look at this, right, so basically you've got a constructor here, and this is a constructor. Say you can construct a package by giving a box, a shared box. Okay, so we've seen this before. So you see the destructor, we're doing one thing because we're dealing with a raw pointer here. And so we're deleting it here. This is the place to deallocate. Okay. And then we have a getter, which is a constant member function. And we have another getter. It returns the next pointer. All right. And then we have a setter that changes this next pointer to something else. All right. So that's package. Next, let's take a look at the truckload. What's kind of let's say this is trucking, is a moving company. We have a truckload abstraction. We're modeling this application. Hey, here's a truckload. A truckload has many packages, and these packages are stored in this data structure called linked list, right? So we don't need to remember. We don't need to know everything. What actually, we just say, okay, I'm just hold on to only the first element in that list, and that's the head. Okay, and then we know everything is chained afterwards. We can actually access every single one of them by following this next pointer, right? And then the very last one will point to no pointer. So there's no more here. So we got 3 packages in this truckload. Okay, so you see the one more higher level container. Okay, the package contains a box object and also point to the next package. And then a truckload has many packages. Okay, they're chained together. So let's take a look at the truckload header. And so we define some bunch of constructors, and we also want the compiler to generate the default one as well, which is just simply the empty truckload. And then you see then we have a destructor here. This only we declare here. We're not implementing inside the class, and that means we implement this outside the class. And let's take a look how it's implemented outside. And then the implementation outside, and then we can just use this outline to find this place. So now, so essentially we're just essentially deleting this head pointer. So remember, we're only remembering the first package as a pointer. And in this case, you need to deallocate. You're dealing with a raw pointer, just remember, then you have to deallocate the memory when you're done. So that's in the destructor. And then you wonder, okay, how come you're just deleting this one, uh, essentially this one object that's pointed to by this head, right? Variable. And then what do you do with the other ones? Are they going to be, stay in your memory and somehow your memory leak? No. So as you see, when you are destroying this package object, right? The package object, when it's destroyed, it will call the destructor of the package object too, right? So the package object also has a destructor. And let's see what it's doing, right? So the package object destructor, what it's doing, this is deallocating the object pointed to by the next pointer. So you see, destructor of this package is going to also destruct the next one, and then it follows. So every single one of them will be destructed. So you don't really need to have, let's say, have a loop and follow through and get everything done. No. So the responsibility of this truckload, you only need to deallocate the first object, the first package, and then every package will deallocate the next package. Okay. And then okay, how come we're not deallocating the box variable? Well, remember that's actually a shared pointer. It's a small pointer, because then that small pointer will take care of itself. Okay, because that has its own destructor that will take care of the allocation of the box object. Okay, so that's truckload. And then, of course, the truckload cannot do much if you cannot manipulate the list, like, for example, adding a package to the truckload or removing a package from the truckload. So to do that, we actually need to maintain a couple more pointers. This is just one way of doing it. Obviously, it's not the only solution. The book also explained another mechanism, at least to deal with how to traverse through the list. Now, traversing the list, the book mentions a very common pattern. It's called an iterator pattern. So you can read up about that, and we're going to actually have more to talk about the iterators later on. Now, so for now, let's say we're going to, okay, we'll still have this head. Okay, we're going to keep track of the head. And then we're also going to keep track of the tail. And then we also have another pointer that's called the current. That basically is the most recently retrieved package. Okay. And how do you remove a package? And by the way, how do you add a package, right? How do you add a package? You actually have two ways to do it. You can add a new package in the very beginning, right? You can add it right here, and then you modify your head and point to that new one, right? Or you add that package to the tail, and then you essentially just modify this next pointer of the last object, last package, to point to the new object, new package, and then you change your tail to point to that new package object, right? So removing a package, and the idea is simple. And here, this is what you started with. This is the current list of the packages. And then you want to remove this one. This is where the current pointer is. And this is the this is the package we're removing, let's say. And then we need to also, doing this traversal, we need to really also remember the previous package too. And then because once we remove this, we need to modify the next pointer of the previous package to point to the one following the one we just removed, yeah? So that it remains a valid linked list, and then with the one of the packages removed, right? So that's kind of the idea. So let's take a look at the code a little bit more. And then, for example, let's take a look at that remove a box. Okay, so there's a couple of lines of code here, and let's see if we can make sense out of it. And so that we're going to look at this. This is the logic we're dealing with. So we're going to maintain a previous pointer like this, and then we have a current pointer. And then we also, when you the remove box takes one parameter, the box to remove. Okay. And so first we need to find where that box is. So you have a loop here, and then you loop this until the current becomes no pointer, so it will stop, right? The stopping condition is this becomes a false. And how does it become false? It becomes false when the current is a no pointer, which means is the end of it. The end of the list is a no pointer, right? So now, so every time it looks at it starts from the very beginning. You see, we initialize the current to the head, and then it was going to examine the current. So it's going to check, is that box the same as the box you're trying to remove? Now this is comparing the address, right? This is pointer equality. And if they're the same, yeah, that's okay, we found the box. Now what do you do now? First, we want to fix the previous box, okay? Make sure this points to the one following, the one we're trying to remove. So this is what we're doing here. So if there is a previous package, well, if your current package is the very first one, the head, that's the one to remove, then there's no previous, so there will be no pointer, right? So that's why we have this check here. So let's say it's in the middle somewhere. So previous is pointing to the previous package, and then we're gonna simply set the next pointer to the next pointer of current, right? You see that the next pointer of current is this package, and then we're gonna point this previous package to the one following. And then we also need to maintain the other pointers that we may need to update them to make sure that this truckload object is still valid, right? So one is the head. So the head becomes what? So the current get next, that becomes the new head, right? Why? How is this important? If the current pointer is actually head, let's say this is pointing at head, well, previous is no pointer. That could be the case, right? The head is the one we're removing. If that's the case, then you have to change the head because that head is removed. So you're gonna move the head pointer to the next one. That's what this is doing here. Now, what if the current package to be removed is the tail, the very last one, and then when you gotta move the tail pointer to the previous one because the very last one is removed, then the last one is the one before, right? Okay. So then if the current is actually the current pointer that we remember on this object, we maintain the state of the traversal here. If that is for actually the current, remember the current is actually the most recent retrieved package. So next time we say I'll get next package, and because we're unloading the truck, and so that is, remember, this is a kind of a pointer that stays at some place. So if that is the package we're removing, and then you better move your current pointer, right? So that's moved to the next one, okay? Advance the pointer. And then once everything's done, and then we first we need to disconnect. We'll set the next pointer to no pointer. Otherwise, if you don't, when you destroy current package, it's going to destroy the next one too. If that pointer is to point to the next package, so then that's not good, right? So you have to set this to no pointer. So that's really the logic here. And if it did not find, here's two more lines. This is the case when we actually found the box and we're manipulating, we're modifying the list. If it did not find it, and then we'll move along the point, we'll advance the pointer. So the previous pointer becomes the current. Current goes to the current next, right? So then this is the while loop here. All right, just kind of I want to go through this. There's a little bit more involved operation in this, all the functions here. So I kind of try to explain this a little bit. Hope that helps. All right, let's go to summarize this chapter. It's kind of a big chapter. Now, hopefully, many of the concepts are not that, sort of alien to you if you have taken a C++ course before. All right, this more maybe is a review, and some of the concepts that maybe you were not familiar with before. Now you maybe learn something new, hopefully. A class provides a way to define your own data types, right? So you're going to use a lot of these, and then really, when you write a C++ programs, you're going to be dealing with the classes the most of the time. You write your own classes, and you use other people's classes. That's kind of the core thing. A class contains member variables and member functions, all right? And then the objects of class are created, initialized by the constructors. So we see what, those are special member functions. We have constructors. And there's also another special constructor, the copy constructor. The copy constructor is a special constructor, is generated if not provided. And then the visibility of members of a class can be private, protected, or public, right? And then we'll also talk about friends of a class. Remember, this is a one-way friendship. And only one instance of each static member variables of class exist, okay? Static member variables, only one instance exists not associated with any object of class. It's tied to the class. And the static member variables are not part of the class object, so they don't contribute to the size. We'll talk about a little size, just kind of for completeness about the size of an object. If your object contains only, let's say, an integer as is a member variable, then the size of this object is just the same size as an integer. There's not much of a difference, except now you've also defined the behavior that's allowed on that integer with the member functions, of course. Then every non-static member function contains the this pointer. So we talk about this pointer. This is just automatically provided to you, accessible in the non-static member functions. But if they are in the static member functions, you do not have the this pointer, right? Remember, the static member functions do not modify state. All right. And then the constant member functions cannot modify non-mutable member variables. So the exception, the member variables that you're able to modify, there are the mutable ones, but but there's only a few usage scenarios where this is useful. So normally you don't really use it. And the user references the class objects as arguments to function calls, right? Can avoid copying overhead. So we talk about this when we talk about when we talk about references. You want to use a reference to class objects, especially if the class objects are complex and the copying cost is high. And then we'll also talk about destructor. That's when the object is going to be destroyed, and this is the function to call. It's called automatically. You typically don't call that in your programming. And then this is also generated if not provided. You can also nest classes. A class, you can have a nested class. Basically, you have a whole class definition inside a class. And the book actually explains a lot more about this, so we don't really, I'm not going to get too much into this because this is, again, one of those features that you're not going to be using a lot, but there are a couple of places where you do use it. But mostly in our examples, we're not going to be using nested classes. So the book does have an example. You can look at that. Let me know if you have questions. So that's all I wanted to share about this chapter. Even though it's kind of a big chapter, hopefully most of the concepts are already familiar to you. And you may also learn a couple of new things and what you're supposed to do and what you're not supposed to do. All right. Thank you.